easy and short and has bonus points that's worth 10 points, which is awesome. One person so far has a grade of 110. So that's always nice. Um, you have no reason to give that one in late. So you have until tonight at 11:59. If you happen to need to get it in tomorrow, I can live with that. But on Friday, if you haven't gotten it in by class, you get a 0, and I'll go over it for people so that it's not ancient history like this one. Okay, so the Z-score quiz. I'm going to share my screen and do all of that good stuff. And of course, it's not showing up. I always forget to hit the little share button. Suddenly, I need a plugin. Unbelievable. We should be good. Okay, I think we're good here. Wow. There we go. You can see that, right? Okay. So the first question was Sandy Slapham. Did you like my names? Are my names fun at least? I see a thumbs up and a smile. I'll take it. 2 out of however many, I'll take it. All right. Cartoon's interested in aggression, and she's got people who have a low aggression score. People have a high aggression score. Questions are, what are their Z scores? What are their percentile ranks? And then questions like, how many people scored between these two, and then how many people scored in the outside 10% of the group. Okay, so one by one, we have Sandy Slapham. Sandy's score was a 13.4 on a scale of, don't tell you the scale, do I? Well, the mean was 10. So Sandy with a 13.4 is up there. So here we go. We have curve, the mean, which is 10.4, I think, 10.8. And then we have Sandy up here with her X of 13.4. Questions so far? I was happy that you almost all drew the picture, because drawing the picture is going to tell you one big thing already. Whatever you get for her percentile rank has to be over 50. Has to be. Here's the 50th percentile rank right here. And you get Sandy up here. And this area, I'm coming up with another color. The green is already 50%. And then you're going to add it to this other area. And that's going to be her percentile rank. Okay, so it's going to be some number higher than 50. As it happens, it's 79%, which might have thrown some of you off because the Z-score was 0.79 also. That's just by chance. Okay, so the answer to that one is 79%. Ish. So I went with ish. You're fine if you came close. Okay, then we have Pat Passive. So Pat Passive, her score is 6.2. Same curve. She's on a curve where the mean is 10.8. She's below the mean with a score of 6.2. Her Z-score is going to be negative. That's the first thing I can tell you. Why? Hey, Isaac, you forgot to put the negative sign, but I didn't mark it off. Why? Because it's below the mean. And you clearly could tell that. I could tell that you, by the other stuff you put there, it was just a slip. but it's important to remember that those negative z-scores are important if you're trying to compute somebody's actual score. Just remember that you need the negative signs, otherwise the math doesn't work. Okay, so with a score of 6.2, her percentile rank is going to be less than 50. How do I know that? Because it's this area here, up to that score is the percentile rank. So if her score is below the mean, her percentile rank is going to be below 50. All of this without maths, folks. This is just concept. This is what I really hope that you can get out of what we're doing today. And as it happened, for those of you who really want to know, her z-score was a negative 1.39-ish, and her percentile rank was around 8.23%. Some of you, instead of getting her percentile rank, got this pink area here and just put that number in for percentile rank. But that's simply the percent between her and the mean. That's not percentile rank. Percentile rank is the blue area up to that score. Okay, next. What percentage of people scored between Sandy and Pat? So you have most of the math you need already. Here's a mean of 10.8. Here's Sandy down here with a 6 point, whatever it is, 6.2. And here's Sandy Slapham up here with a high score of 13.4. You already know their z-scores. We have 0.79 over here. And down here we have z equals negative 1.39-ish. And you also already have this red area because you had to do that for the first problem. Okay, so what percentage of people scored between them? It's going to be the red area plus the pink area. That's the scores between them. You can see one scores at the bottom and one scores at the top of that range. And you add those two areas together. And when you do that, you get about 70%. And it looks like it's about 70%. I actually drew a picture sort of to scale for once. Okay, moving on. This is the hardest question for a lot of you because you didn't have the earlier answers to rely on. So what two scores are going to cut off the outermost 10%? There's going to be a low score and there's going to be a high score. And you have notes that you could have gone through to see how we did this problem, which is what I'm guessing most of you did because we did one a lot like this. And so the outermost 10% means we want to keep the middlemost 90%. And that means that that 10% is split between the two edges. The outermost 10%, half over here at 5% and half over here at 5%. And then you use the table with the 5% in column C to find your z-scores. And then once you have the z-scores, you use this formula to find the scores, and this is where that negative sign matters. And you find a low score here, and you find a high score here, and you answer the question with them. And many of you got this one right, and I'm proud of you because this was the one we only went over it once, and it was the hardest of the bunch. And the answers are, there's a lot of little tweaks here with rounding and exactly where you were looking on table, but 6.63 and 14.97 or 5 point something and 15 point something were the answers right in there. People use slightly different raw numbers going in because of legitimate reasons. So that was the answer for that. That's how you approach that problem. Any questions other than I still don't get this and I hate it? Like any specific questions that you think maybe I marked it wrong or something like that? Can you see the red marks that I put on your quizzes? Okay, because that was my first time actually getting the software to work. So that's slightly miraculous. One other question. Do you see me in a small box on your screen, or is it just the white screen? Okay, just checking. Okay. All right, so that's the quiz. I'm moving us on. So we've done probability, we've done that. We're going to talk next and learn next how to compute what officially we call confidence intervals. The literature is full of talk about confidence intervals. Hold on, I'm going to stop sharing my screen for a second. It's full of what we call confidence intervals in the professional literature, you know, the journals. But out here in the public, on news sites and on just general sites and in writing of all kinds of essays and articles, what you really are hearing is not the confidence interval, you're hearing the words margin of error. Margin of error is a confidence interval. It's the same thing. And I found for you a current example of confidence interval, but you have to remember that they're saying margin of error. But I just to give you the concept of what we're trying to do. And basically the bottom line is we're trying to come up with a range of scores where we think the right answer is. So when you ask people, how much do you like, I'll go for my last class, chocolate ice cream on a scale of whatever to whatever, then let's say from 0 to 100, how much do you like chocolate ice cream? And the answer comes out to be 80. Is the right answer in the population out there really 80, or is it somewhere between 75 and 85? Can I be 95% sure that somewhere between 75 and 85% is the answer of how much people like chocolate ice cream? This matters if I'm a maker of ice cream. I need to know how many machines to devote to chocolate, right? If I find out that the answer's 80 and margin of error is really small, then I know I can trust that number 80. But if the margin of error is really wide, that means it could be anywhere between 65 and 85, and that's a little more iffy. I mean, that means I might need a lot more chocolate or I might need a lot less. I need a better way to measure it. So I can't trust the information as much because it's too wide of a range. That's what margin of error is about. And if you have two questions like, would you vote for Trump? How likely are you to vote for Trump? How likely are you to, tell me you're not eating ice cream, Sam. No, it's cereal. Okay. How likely are you to vote for Trump? How likely are you to vote for Biden? And if you see that they have separate means, but their margins of error overlap, that's where the people running the campaigns start to sweat, right in the overlaps. So I've got an example of what of somebody explaining this far better than I can actually from, I think it's NBC News. So hang on, I'm going to do a share my screen with my web browser here in a minute. Okay. I need somebody to speak up if you can't. Hold on, I have to escape from share my screen. I need somebody to speak up if you can't hear the audio or you can't see the video as soon as I start share my screen here, okay? So share screen, my desktop. Hello, everybody. Watch, you'll see everybody. A mess, right? So we don't need this open. This is the one. I'm turning it into full screen. I'm going to hit play. Let me know. Oh, I got to make you guys go away, don't I? That's as close as we're going to get, I think. Okay, let me know if you can't see or hear her. Is it good?
I can't hear the video.
Really? Oh, maybe it's because I have earplugs plugged in. Hold on. Again, let me make sure that my sound, let's just try it like this, see what happens.
Tiny text that says plus or minus some such percent. That's the margin of error.
How about that?
Yep, that's good.
Okay, I'm starting it over, if I can. Okay, here we go.
When you see the results of a poll on TV or on the internet, there's usually some teeny tiny text that says plus or minus some such percent. That's the margin of error. But what exactly does that mean? Are pollsters saying that they might actually be wrong? Margin of error has to do with how confident a pollster is that the number of people they polled represent the whole population that they're trying to figure out. Okay, let's start at the beginning. A pollster sets out to try to figure out the answer to a question. Let's say we're trying to figure out how many registered voters in America think that baseball's opening day should be a federal holiday. Go Nats! There are 140 million registered voters in America. We can't exactly ask every single one of them what they think. Not really practical. But we can pick 1,000 people as a model of the population and ask them what they think. That's our sample. Now, a good sample population would include demographic information like the age, income, race, gender of participants. You got the idea. There are a couple of ways to keep the margin of error low and to make a pollster's confidence go higher. The more people you include in a sample, the higher that confidence is going to be. Okay, so in an NBC News Wall Street Journal poll, our margin of error for the registered voter population is usually around plus or minus 3 percentage points. We get that number by plugging in our sample size and some other numbers into a specific formula. If we're short on time or cash, we could do the same survey with only 500 people, but our margin of error would go up to 4%. And if we did it with only 100 people, the margin of error goes up to 10%. And that, not very helpful.
First, with President Trump still recovering from coronavirus, about to hit the campaign trail, and the confirmation hearing for Supreme Court nominee Judge Amy Coney Barrett.
Honestly,
White House correspondent Hallie Jackson joins us on this Monday with both stories. Good morning.
Jeez. Okay, back to us. Did that help at all? She went fast, really fast. So the real thing is where do they come up with that 3%? Like how does that she does that magic box thing where, and we run it through a specific mathematical formula. That's what we're going to be about. I'm sorry to tell you, that's what we're going to be about. The boring part, the not fun part. I think you're thrilled. I know, even I find this topic irritating, and for years I skipped it, but the problem is that now confidence intervals are really big in journals. People's articles are getting turned down because they didn't compute their confidence intervals and include them. How sure are you about this mean? How likely are people to be different from the mean is important. So what we typically want to do is we typically want to be able to be 95% sure when we say a sample mean that it reflects the population. That's standard in social science. Sometimes when the stakes are higher in certain ways, which I'll explain as we go along in the course, we want to be 99% sure sometimes that when we get a mean correct, that we're 99% sure that we've got the right number. Think about us working with ways to tell if somebody is suicidal. My partner does anti-suicide stuff. So ways to tell if somebody is suicidal. Let's say we have a measurement scale. We would like to be 99% sure when we have somebody score low on that scale, that their answer truly is that low, that their actual state is truly that low. So it matters at the individual level and it matters at the large group level. The one that she's talking about is a large group level. And that's what we typically think about in most of the field of psychology, which is, does my sample reflect the population? I have a theory, I'm testing a theory, I can only use a sample. How sure am I that my results reflect the population? Just like in politics, how sure am I that when people say they're going to vote for Biden, that reflects the rest of the state of whatever, Georgia, whatever. Right now, we have enough toss-up states that we are seeing very high number of articles with margins of error being reported in the big newspapers. You see whole articles about what is the margin of error in the Times, New York Times, and in the Washington Post. I have a cheap educator's discount for both of those. And I'm actually seeing articles about don't forget about the margin of error, or don't believe the margin of error, or example of the margin of error, or how to understand it. There's lots. So if you're interested in looking at it from contemporary questions, just look at those two sources if you can get to them. They're paywall, right? So if you want me to grab you an article, tell me and I can grab you one from them. Okay, so I'm just trying to kill my web browser to get it out of the way. I'm trying to get rid of a lot of stuff to get it out of the way. And my screen's gotten way too complicated. And I might have to share it, so hang on. I think I'm there. This is very nice. It's just me and you guys again. It's lovely. Okay, so now that you know what a confidence interval is, let me start explaining how we get there. So hold on, I just put my notes over here, but now I don't see it. Here we go. And just once more, the whole reason for doing this is because the sample mean isn't exactly the same as the population mean. It isn't. If that were true, then we wouldn't need to do sampling. We would know. So we wouldn't need to do experiments if we had exact correlation between them. So because they're not exactly the same, we have to do science, and then we have to be able to be a certain degree of certainty about our results. So I'll give you a definition of a confidence interval. It's a range of scores within which we are reasonably certain the population mean lies. A range of scores within which we are reasonably certain the population mean lies. In other words, a range of scores, and we can be 95% sure that somewhere in that range is the population mean, or 99% sure that somewhere in that range is the population mean. So a range of scores within which we can be reasonably certain the population mean lies. Was that you, Elijah?
Yeah, I was just going to ask if you could say it one more time.
Yeah. Do you want to hear it one more time now?
Yes, please.
A range of scores within which we can be reasonably certain the population mean lies.
Thank you.
Sure. Another way to say it is it's a range of scores within which we can be 95% certain we'll find the population mean, or the population mean exists. Something like that, if that's an easier way for you to hear it. Another way is we can be 95% sure that the population mean is somewhere in this range. We use our sample, mean, and standard deviation to compute it. And then we have that range, and we can be 95% or 99% sure that somewhere in that range is the true population mean. Does that make sense? It's very vague. It sounds very iffy and theoretical and abstract. But looking at politics now is your best shot at understanding the reality of it. And always think of it as margin of error. Who follows baseball? Anybody? What sport do you play? Lacrosse? Okay, so name a well-known lacrosse team that plays a lot of games. Like on some professional level. Is there anything in Europe?
It's in America usually.
Okay. So,
Um,
all right,
the
so-
most
so
popular.
in your career as a college athlete, how many games do you figure you play, Sam?
Usually we play like 16 a season.
All right, so 16 times 4 is 64.
Sure.
Yeah, I got it. 64. Okay,
Yeah.
so let's say that you were a really kick-ass high school lacrosse player. And I wanted to figure out how you would do in high school, in college. And I had some way of figuring it out. And what I would probably come up with is the number of games that you would probably be winning if you were on a team, my team, say I'm a college coach. And out of 64, I'm going to predict 40. But I can't be exact because it's a prediction. If I use the formulas for confidence interval, what I end up with is, all right, I'm thinking if this guy Sam is on my college team, we'll be winning 40 out of 64, which is decent. And but really I can be 95% sure that it's somewhere between 35 and 45. Is that as decent? I don't know. Right? So, and then if I wanted to be 99% sure that I had the number right, I end up having to go wider. If I want to be 99% sure that I've captured the right answer, maybe I have to go from 40, maybe I have to go from 30 to 50. Right? Now I have more confidence that the number's somewhere in there because I widened it. I widened the range. Did that make sense with a real example from real life? What, Isaac?
So I guess the way that so it's using a sample
Yep.
and it's how confident you are in that sample representing the population.
Yes, but
The samples mean, it's how confident you are in the sample's score or mean representing the population's mean.
kind of, not exactly. Instead of that, we preset how sure we want to be. And when we do that, it creates a range around that mean.
So when they say plus or minus 3,
Yes.
and the percentage is 46 or something,
Yep.
so the score is going to be in between 49 and 43 kind
Exactly. We can be 95% sure that the real answer is somewhere between 43 and 49. Our sample mean comes out to be 46, and we can be 95% sure that the population mean is between 43 and 49. So people are telling us how they feel, and we get an answer of 46 out of 100, whatever. But really, the real answer is within a spread of numbers. Did that help? You're good. Okay, so now that we know what we're trying to do, we're going to get down to the ugly part, which is the math, which is truly not something you're going to like so much because it's math. But we're going to get past this topic and then we're going to get into harder math. So it's okay. This course just keeps getting worse formula after worse formula after worse formula. And we have a couple of them that are really short formulas. But when you look at them, you realize you don't know what any of the letters are. And so you have to go find them too. It's just nightmarish. Sorry, I like it, but most people can't stand it. So hold on, let me share my screen. Okay. All right. So we are going to be trying to compute what we call the 95% confidence interval, the range of scores that are going to be around the sample mean, within which we can be pretty sure the population mean lies, so we're going to create the 95% one. So we're going to create the range of scores so that we can be 95% sure that the population mean is in the range.
So it's not going to be exactly the same as the sample mean, but it's going to be within this group. And we get that because we know the sample mean and we know the standard deviation and we know that damn curve. So we can compute that 95% spot. Just like the opposite of the last question on the Z-score quiz. Or just like the third question where we wanted to get the groups in between two scores. That's what we're doing now. We're pushing the scores out till we hit that 95% so that we have 5% in the outside. So we have 2.5% at the bottom, 2.5% at the top. We're trying to find the two scores that set that part apart. But we don't get to use Z-score because we're talking about a whole group of scores. A sample mean, not an individual score. So Z-scores are about individual scores. Once we start bringing it up to a group, we have to use confidence intervals, and we're going to be using something called T-scores, which is basically the same concept as a Z-score, but we're going to use T-scores for this and for t-tests, which you've probably seen in articles. There's 3 kinds of t-tests that we're going to be using this for. So there's a new table that I may or may not have remembered to put up on the Canvas page. So I may be stopping us before we get too much further here. All right, you may be taking a 10-minute break while I try to find, I have a paper copy of the table here. I might have to scan it. Okay, so what we're looking for the 95% confidence interval, you have to imagine that that we already have a sample mean and population, sample mean and standard deviation. Here's the formula for finding it. Isn't that pretty? Who likes it? Who thinks it's the best formula they've ever seen? Nobody, right?
Is that a 5 or S for standard deviation?
That's an S. The 5 is after the T, T.05. Now, before we go any further, we're going to need to find that T value, and it's found in a table, and I don't think that the table's on Canvas. So take 10 while I get set up for that, okay? We'll be back. I'm going to stop. Somebody tell me to hit the recording again, please. I'm putting, Heather, I'm putting you in charge. You're the top of the pictures right now. Okay, thanks. Sometimes I need it, sometimes I don't. It's been about 10 minutes. Still no Joe. He's got a recording. Okay, so going back to the formula. You won't be able to see me because now I'm going to do share screening with this math stuff. AirPlay's working pretty well for this class. I'm happy. I'm also happy I got a new iPad just before the semester started because my old one wasn't working for this stuff. Okay, so here's this formula, and I think the best way to do this is to just quickly show you what we're trying to do here. And this is going to feel a lot like Z-scores, and that's a good thing. So what we're trying to find is, let's say this is the sample mean. And what we really want to know is a 95% sure range of the population mean. That's what we're really looking for, right? So to do that, we have to tentatively, we're doing it. So we're using the sample mean, and then we need to find some number up here and some number down there, and within which we have 95% of people. Which basically means we're looking for the numbers so that there's 2.5% over here and 2.5% over here, because we want the middle 95. That's how it's like z-scores. This is why we make you do z-scores, so that these concepts of closing out the tails of a distribution make some sense to you, and how we think about percentages. Because you always have to remember, when you're looking at a normal curve like this, you're always looking at scores down here, and you're always looking at the frequency over here, which is, imagine people standing on each other's shoulders, teeny tiny little people all in these areas. And you can fit more of them closer to the mean than you can out here, right? So we're looking for the middle 95%. A lot of them are going to be near the mean, and how far spread out are they before we know we've got about 95%? That's basically the concept that we're trying to achieve by using this amazing formula up here. It's going to give us, because it's got a plus and a minus there, it's going to give us the low number, and it's going, this one, and it's going to give us the high number over here. And it looks a lot like z-scores. Instead of z times s plus the mean, we have t times almost s plus the mean. And we subtract that from the mean and we add it to the mean. That's what that plus and minus means. So the concept is a lot like how we did z-scores. Z-scores are for individuals compared to a mean, and t-scores are for a group compared to a population mean. Okay, so it's for looking at samples instead of individuals. For some reason, we have to use t-scores instead of z-scores, and that reason is not important right now. Okay, let me get rid of these pink lines so you can see the formula more clearly. Hang on a second. I tried to do this so that, there. Okay, so I want to see, there's got to be a way to capture this formula and move it below this picture. Hang on a second. And then I want to erase all this other stuff here so that I have this to work with without all the picture in the way, because when you try to do the math, I want it all on the same place and I don't want to have to rewrite the formula. So hang on. Okay. Look at that. She can use technology. All right. There's our formula. And we're going to try just with a few problems to get you used to doing this. This is, once you know how to do this, that's the whole game. It's not that hard. And I'm going to put in a quiz. It's just going to ask you to compute confidence intervals. Okay. We'll see what the grades look like before I decide whether or not to include them, because it's only going to be 2 questions. So just like, I'm going to give you some numbers and you're going to compute the 95% confidence interval. You're going to compute the 99% confidence interval. I'm confident that almost everybody can get 100, but let's see how that goes. Okay, so I need to find a good problem here, so hang on. And in the process of that, you're going to learn how to use the table. Okay, let's say that I have a group of 16 people. So N is 16. And their score on a scale of 1 to 7 is how confident are you that we're going to have a vaccine for coronavirus by Christmas, by the end of the year, okay? So the scale goes from 1 to 7. So, or let's say 1 to 10, just because I don't remember what the confidence interval comes out to be. Yeah, it could be 1 to 7, doesn't matter. Big scale compared to the number. And we check with these 16 people on their scale, let's call it 1 to 7, and their mean, they're not particularly confident, comes out to be 2.9, where is it? 2.96. And their standard deviation comes out to be 0.34. Okay, we can get that the normal way. You get a list of scores, you throw it into your calculator, it gives you the mean, it gives you the standard deviation, or you do the math. We have a formula for each of them already. So these are not mystery numbers, right? These are real numbers from the 16 scores. You can do that. You can do that without having to lift one math muscle by just putting them into a calculator and hitting compute or whatever you hit. One var. Okay. So we have the mean. We don't have this T thing, and we don't have this S with a sub X. That's not standard deviation. That's not this S. It's S with a sub X. It's called the standard error. It's what we do when we're going to be comparing samples to populations. And it's equal to the standard deviation over the square root of N. S over the square root of N. It's what keeps us from being less confident about smaller samples. The denominator gets smaller and smaller, so our confidence gets less and less. The larger sample you have, the more you are confident in a smaller group of numbers. The fewer people you have, the more you're not sure you have the right numbers, and your range gets bigger and bigger. For being 95% sure, you need a wider range. If you have a lot of people, you don't need as wide a range because you've sampled so many people already. You're pretty sure of your answer, right? That little S over the square root of N is what makes that happen. Okay, so the only thing missing right now is this T. So let's look at this problem. So 95 CI is equal to plus or minus, I'm going to take that out of the parentheses, T 0.05 times the standard deviation over the square root of N. So 0.34 over the square root of 16. And we're going to get that, and then we're going to add that. We're going to get the plus of it, and we're going to get the minus of it. And we're going to add that to the mean, which is 2.96. All right, so the next step we know the, I'm just writing different ways that you can see how this is expressed with the brackets and the parentheses so that you can figure out which way, this is the actual correct way with the one I'm doing now, but you can see all the different ways that you see it expressed in formulas and websites and all of that. So 0.34 over the square root of 16, don't bother. I know you know how to do that math. It's 0.085. Let's leave all the numbers in there. We'll pretend that we're a calculator for now. All right, all we're missing is T. Like Z, we get T from a table. And if this is hard for you to remember how to do this, just remember T for table. I had a very nice teaching assistant when I was an undergrad. She kept telling us all this like alphabet ways to remember math stuff. It was ridiculous. Okay, so now we're going to look at the table to find T. Hang on while I find it. Actually, I have to stop the screen sharing and go to another one. Hang on. Okay, focus on the white document. Here we have a T table. It's a very scaled down version of all the different kinds of columns that you can have in a T table, because these are the only ones we need. Notice the 0.05 column and notice the 0.05 in our formula for T, T.05. That means this third column in here. Okay, so we know that this is our column because this is saying the T that we want is for being 95% sure we're correct. This is for like the amount of error we're willing to have. That's called the standard error. We're going to go here, and what we're missing is how far down to go. We know our number's coming from this column, but what we don't know is how far down to go. We don't know how far down to go because we don't know the value of that column, the degrees of freedom column. DF stands for degrees of freedom. Now, I have to do a whole aside that's not actually part of computing confidence intervals. I have to explain degrees of freedom. This is irritating, I know, because we're in the middle of a problem. But if I don't explain it now, none of this will make much sense for like the next literally month. So, degrees of freedom, the definition is in a group of numbers, it's the amount of them free to vary given certain restrictions on the data. I'm going to say this again. In a group of numbers, it's the amount of them free to vary given certain restrictions on the data. Degrees of freedom requires me to go back to the other kind of sharing. So hang on while I do that. Come on. Okay.
Dr. Maluso,
Yeah.
could you explain degrees of freedom one more time?
Yeah.
Sorry.
Yeah. I'm going to give you really nice examples of it, but it's the amount of numbers free to vary given certain restrictions on the data.
Okay.
So let's say we put some restrictions on the data that n is equal to 5. And that the mean is equal to 3. We often have restrictions like this on the data. In fact, in this case, we also have it. We have n is 16 and the mean was whatever we said it was, 2.96, right? So those are restrictions on the data based in reality. And here we have a pretend group of numbers. So we have n is 5. How many of them are free to vary given these restrictions? This, I think, will work with Zoom. Sam, give me a number, any number from negative 100 to positive 100, whatever you like.
4.
Okay, that was simple. Jack, give me a number.
26.
Excellent. Grace, you got a number?
I don't know.
Well, think of any negative number from 0 to negative 100.
Negative 13.
Okay, thanks. Elijah, any number?
34.
Okay. So far, notice these have been free to vary. Why? Because we still have 1 to work with. We still have this one, thank goodness, because we need to make sure that in the end, these 5 numbers end up with a mean of 3. How many numbers are free to vary given certain restrictions on the data? Right now, the answer is 4. All these first 4 can be anything they want because we can always fix it with the 5th one. This can't be anything we want. I can't say 99 just because I like it. We would have to compute what this is. Hey, let's do that. Nah, I don't want to do that. So do you realize though that this would have to be a very, like only one number can be here and make this n equals 5 true and the mean is 3 true. The first 4 could be anything they want. But that 5th one has to fix it. It's the cleanup. So in this case, in a simple list of numbers where the restrictions are, we know n and we know the mean, degrees of freedom is equal to n minus 1. That 1 has to fix it. The other 4 are good. If we had a list of 10, we could go with 9 random numbers and the 10th one would have to fix it to make the mean be whatever it is we said the mean was. Does this make sense? Tell me, somebody tell me if it's not making sense.
I'm a little bit confused.
All right, Elijah, give me a low number n, something below, some really small number, like bigger than 2 though.
3.
Excellent. Okay, and give me their mean. On a scale of 1 to 5, give me a pretend mean.
2.
Okay, these are the restrictions on the data. We had asked 3 people on a scale of 1 to 5, how do you feel about, what was it, baseball's opening season, right? Was that the one? So how do you feel about baseball having in person this year? And on a scale of 1 to 5, the mean of these 3 people's answers was 2. You with me so far, Elijah?
Yeah.
Okay, good, because they're yours. So I'm happy to make sure they work for you. Okay, so now we have these 3 people. Elijah, make up the first person's answer on a scale of 1 to 3.
1.
And the second person's?
3.
Okay, now, can you just make up the third person so that the mean comes out to be 2? Or is there a specific number that's going to work there?
There's a specific number, I'm guessing.
And that's, yeah, good guess, because it sounded like a good answer, doesn't it? That's what I'm talking about here. The degrees of freedom are the numbers, the amount of them that can vary. Given these restrictions that n is 3 and the mean is 2, only 2 of these numbers can vary. This third one cannot vary. It's a specific number. 1 plus 3 plus something divided by 3 equals 2.
right?
Yeah.
I guess the answer is 2. Just a hunch. That's why I wanted a low number so I could do it in my head. So it has to be 2. It can't be anything else. So the number available to vary is 2. Degrees of freedom equals n minus 1. Degrees of freedom in this case equals 3 minus 1, which is equal to 2. It's these two, the 2 that are allowed to vary. Over here, degrees of freedom equals 4, because this one over here is not free to vary, but the other 4 are. Did that help?
Yeah, it did. Thank you.
You're very welcome. Anybody check, you good? You look so damn comfortable, I cannot stand it. That thing's fuzzy too, isn't it? Man, you're killing me here. Look at me in an office-like setting in my own damn house. I'm moving to my lounge chair, you guys. This is not fair. I'll put my dog on my lap and relax around here. Look at you all. Heather, you're the only one that looks like you're sitting up. And no, actually, Sam, other than his Mick Dry, is that what it is, Mick Dry? Other than that, back
Yeah, I
there.
was hoping you wouldn't notice it. But...
Oh, okay. Yeah, the big beer bottle over your right shoulder. I won't notice that at all. Look at it.
I didn't realize it was there until like the
I
third
don't
day of
care.
class, but at
Doesn't
that
bother
point,
me
I
if
didn't
you
really
like.
want to take it down. So
Is it
just
really Mick Dry though? Like you like?
Yeah, Michelob Dry.
How old are you, Sam?
20.
Yeah, so when you're legal drinking age, I suggest you go with a beer that's got something in it, like maybe Guinness, like
Yeah,
something, or a stout, something that's not what we used to call pony piss.
All right, I'll take your.
It's just an advice for when you're of legal age. I'm just saying.
That was a gift from one of my buddies last year who graduated.
Okay, I'll take that answer. That's good.
But we can have it in the room because I'm 21, so it's fair game.
That's fun. I like that. I suggest you get better beer. Okay, so that's degrees of freedom. Now, why did I go through degrees of freedom? Because this formula needs a T, and the T needs degrees of freedom. You look at your T tables that you can see, or do you want me to put it on the screen again? I'll put it on the screen again. Hold on, I got to stop this sharing. I got to open up my other screen sharing. I'm getting better at this. This class today is the one. Can you see my screen? Doesn't look like it. You're seeing this table here?
Yeah, we can.
Okay. All right. We're looking for a T value in the 0.05 column. That's going to be our T value. This is filled with T's, but we have to know how far down to go. So we have to look in the degrees of freedom column, and we have to go down as far as n minus 1. The problem we're working on says n is 16. So what's degrees of freedom? Somebody say it out loud.
How much you can vary. Is it always going to be?
It's going to be 15.
It is, Isaac. And the answer to your question, check, is yes. For our purposes, when we have a one list of numbers and we know the mean and standard deviation, it's always going to be n minus 1. But we're going to get into more complicated stuff where we have 2 independent groups of people. And we're going to end up having to find a t-test for that situation. It's not going to be n minus 1. It's actually going to be each group's n minus 2. We'll get into that later. It's basically the same concept, it's just written differently. So, but for our purposes, for a while now, it's going to be n minus 1. And for confidence intervals, it's always n minus 1. All right, so we go down to 16 in this table, and we're using column of 0.05 because that's what we set for T, because T of 0.05 means we're working on the 95% confidence interval. We can be 95% sure that our 2 numbers contain the population mean. So we go down to 15, and what do you get for T? Isaac, finish it up. What do we get for T?
It's going to be.
Isaac wants me to say, what do you want me to say?
2.1315.
2.1315.
Yeah, okay.
You guys are in the same situation. I feel for you. It's a pain in the neck. Okay. Now I'm going back to share the screen with the math on it. So hang in. Done with the T-table for now. And move into this other kind of sharing. Okay. So now, unfortunately, I have been writing way too big. It won't shrink. There we go. I'm going to try to write a lot smaller here, but also seeing this formula. All right, what we need to do now is we need to substitute in that t, which was 2.1315. So it's 2.1315 times 0.085. Oh, yeah, okay, never mind. I'm trying too hard to write small. It's not working very well. All right, hang on, I have an idea. All right. You can see that, right? Now we have all the parts of the formula and we just need to do the math. So when you multiply that first part together, the t and the standard error, you get 0.182. Let's call it 0.18. And I'm going to do this so you understand it better. Plus, 2.96. How do we get the two numbers that describe the confidence interval? We take 0.18 and we subtract it from 2.96 to get the low number. And we add it to 2.96 to get the top number. That's what this plus and minus stuff is about. Okay, so we get, it's like, depending on how you've been rounding, 2.74 and 3.11 right in there. I put them apart because here's how you report a confidence interval. You say confidence interval 95% equals 2.74 is less than or equal to the mean, the population mean, mu, is less than or equal to 3.14. So in other words, my population mean is somewhere between 2.74 and 3.11, and I computed that after a sample of 16 people whose mean was 2.96. And in the end, I'm pretty sure, 95% sure, that the population mean is between 2.74 and 3.11. Margin of error, it matters. It matters a lot if your answer is going to cause somebody to create medication, to spend money, to predict an important thing. Margins of error matter. That's why we have to do them these days, because they matter to the online journals so that people have a much better sense of how sure were we when we did this wonderful sounding experiment that our results are meaningful. Okay. Class time's over and we're going to do some more of this on Wednesday, and then Friday will be asynchronous. You'll be working on some of your own. And I think what I'll do is I'll create a 4-problem quiz so that way your grades don't tank quite so fast. By the way, many of you did really well on that Z-score, so good for you. The others of you, be careful of small mistakes. Okay, go have a life. I will see you all on Wednesday. So long.
Bye.